Radio frequency powered devices are a promising IoT technology that may begin a new era of self-sustainable communication systems. These RF powered devices can communicate with each other using the low power they leverage from RF sources using Wi-Fi backscatter technology. Additionally, the ability to harvest power from RF signals allows them to run without a conventional power source. The paper Wi-Fi Backscatter, Internet Connectivity for RF-powered Devices explores the idea of using existing Wi-Fi infrastructure to connect RF-powered devices to the Internet. RF-powered devices are limited by the amount of power available to them from ambient RF signals. This amount of power is significantly less than the conventional low-power Wi-Fi transceiver and thus does not have enough power to speak the Wi-Fi protocol. To combat this issue, a Wi-Fi backscatter communication system must be implemented. The researchers designed an uplink and downlink communication channel that allows information to be sent between Wi-Fi backscatter tags and the Wi-Fi devices. The feasibility of this device is tested through a hardware prototype which achieved data transfer rates of up to 1 kilobit per second within a range of 2.1 meters from the Wi-Fi device. Furthermore, the paper Ambient Backscatter Assisted Wireless Powered Communications expands on the study of integrating ambient backscatter technologies into IoT devices to communicate with wireless powered communication networks. The researchers confirm backscatter communication is an ideal solution for low-power IoT devices as the typical backscatter transmitter consumes less than 1 microwatt of power. This low power consumption lends itself to work perfectly for RF powered devices as they typically can harvest from 1 microwatt to tens of microwatts from RF sources.
The researchers found that the backscatter tag design is capable of detecting modulated Wi-Fi channel information with power consumption as low as 1 microwatt. The algorithm for CSI modulation was also found to be effective up to ranges of 65 centimeters and progressively deteriorates with increased distance. An alternative design explored, however, was found to increase the range an additional 2.1 meters. Uplink bit rates reach between 100 and 200 bits per second, operating only on ambient Wi-Fi transmissions, and found that the bit error rate and range improves as packets per bit increases. It was also determined that CSI performed significantly better than RSSI at decoding at lower error rates. The downlink was also found to achieve bit rates up to 20 kilobytes per second at 2.13 meters and managed to achieve a false positive rate of less than 30 an hour. The researchers found that the backscatter tag design is capable of detecting modulated Wi-Fi channel information with power consumption as low as 1 microwatt. The algorithm for CSI modulation was also found to be effective up to ranges of 65 centimeters and progressively deteriorates with increased distance. An alternative design explored, however, was found to increase the range an additional 2.1 meters. Uplink bit rates reach between 100 and 200 bits per second, operating only on ambient Wi-Fi transmissions, and found that the bit error rate and range improves as packets per bit increases. It was also determined that CSI performed significantly better than RSSI at decoding at lower error rates. The downlink was also found to achieve bit rates up to 20 kilobytes per second at 2.13 meters and managed to achieve a false positive rate of less than 30 an hour.
Time to main signal for an 802.11 AC very high throughput transmission with 7 packets and a 30 microsecond idle period between packets. Replication of the raw CSI measurement of Wi-Fi packets observed in the paper showing binary modulation. Simulation of the downlink channel on the backscatter tag side where it conveys data by encoding bits with the presence or absence of Wi-Fi packets. The paper provides insight into possible usage of RF-powered devices and Wi-Fi backscatter. It can easily be integrated with current networks. The negligible power consumption, 1 microwatt, exhibited range, 2.1 meters, and maximum bit rate, 1 kilobits per second, achieved by the prototype demonstrates this technology's potential. The prototype provides sufficient proof of concept and still has the capacity to be improved upon. The tag has the ability to communicate within the Wi-Fi range despite lacking the capacity to decode or encode Wi-Fi packets. There is the possibility of communicating in other RF ranges or with other RF devices. Basic factors and limits of the backscatter tag, such as the distance it can communicate, the size of the antenna, the average power consumption, and both the firmware's and hardware's capacity for decoding, encoding, and transmitting data all have the potential to be improved. The configuration is of a single Wi-Fi helper creating RF waves and the tag using the waves for power to communicate with the Wi-Fi reader. There is potential for further investigation with more elaborate combinations to simulate a commercial environment. Research could be made into the storage of energy converted from RF absorbed by the backscatter tag. While more expensive, developing network devices that accommodate these RF-powered devices may lead to an overall net benefit.